Hi everyone and welcome to another part of Applied Mathematics. Today I'm going to be introducing the topic of vertical motion under gravity. Alright, so it's going to be a unique part. I believe I'm going to explain it to the basic core for you to understand even better. My name is Emmanuel Olega and I'm a math teacher and a software engineer. What I want to do through this video is to help you out to have a better understanding of your applied math as you prepare for your UNEB exams as a senior 5 or senior 6 A-level student. Alright, let's get into today's video. Alright, so now we're going to start with another topic. So today we're going to be looking at vertical motion under gravity, and this is going to be one of the key parts of kinematics. So this is a topic I would suggest someone learns after they've had a knowledge of motion in a straight line. Alright, so let's learn something new. Alright, so vertical motion under gravity is what we're looking at. So the movement of a particle whose vertical motion is altered by the presence of gravity is referred to as motion under gravity. So now the difference with this and linear motion is right now, instead of acceleration, we shall be dealing with gravity. Alright, so we're going to be dealing with gravity. So now there are two ways to look at vertical motion under gravity. So there is what we look at as downward motion under gravity. So it's like a body under free fall. So a body that's basically falling. So imagine you held a ball from at the top and then you just released it and it just fell freely. Of course, it would move in a downward motion under gravity. So that's what we look at as the first case. So suppose a body of mass m kilogram is dropped in such a way that it experiences negligible air resistance. The body will move in a vertical straight line and the only force acting on it is its weight as below. So this is an illustration of that body. So this is what will look like. So it's like a body with a mass m kilogram, and then right now you can see that there is no upward motion, so it's 0 newtons at the top. So it's only being moving, it's the only force acting on it is its weight, and of course the weight is mass times gravity. That's why we call it mg newtons. And then we imagine that the acceleration is in a downward motion. But in such a situation, from Newton's second law of motion, we can see that force is equal to mass times acceleration. But also, mass times gravity is equal to 0 is equal to ma in this case. So now in this case, we know that two opposite forces are equal. So you get what we have here to the 0 newtons that we have at the top there. So we can equate it. So now instead of ma, we can substitute that with mg. And then we can actually see that mg is equal to ma. So if you equate mg as being equal to 0 and you make g the subject, you can actually see you'll have 0 times divide by m on the other side, of which the answer will be 0. And then we'll remain with mg being equal to ma, and then we can actually see that the m's cancel, and therefore we remain with g being equal to a. So in this case, that's for downward motion. You can actually see that when the body is falling downward under gravity, so for the first equation of motion, remember the first equation of motion was v is equal to u plus at. Now we place a g where we have the a for a body under free fall. And also it means that when the body is under free fall, also the second law of motion changes. It becomes ut plus a half gt squared. And then definitely that means that the third equation of motion becomes v squared is equal to u squared plus 2g s. Now remember, this is exclusive to only free falling. Before we look at the other case, when a body is projected vertically downwards, it's subjected to an acceleration 9.8 meters per second squared. So this is the equation of acceleration, but we've said that acceleration is equal to g, so you can see that g shall be equal to 9.8 meters per second squared. So the motion for which the body is acted upon by gravity without other opposing forces like air resistance is called free fall. Alright, let's look at the other case. So the other case is upward motion under gravity. So this is more like you throwing a ball upwards, or a stone, or anything you can actually throw. So suppose the body of mass m kilogram is thrown upwards in air such that it experiences negligible air resistance. The body will move in a vertical straight line and the only force acting on it is its weight. Alright, and since we are looking at a motion moving upwards and the body is not in equilibrium, we can actually see that we'll have 0 minus mg. So from Newton's second law of motion, we can actually see that F is equal to ma, and that will be the same as 0 minus mg. So we're going to substitute that for F. So it's equal to 0 minus mg. And then A shall be equal to negative g. That's what happens if you cancel out the m values, and we shall see that the acceleration this time will be a negative when a body is moving upwards. So that's for downward motion. We're going to have negative gravity. So the first equation of motion will be v is equal to u minus gt. S is equal to ut minus a half gt squared. And then the third equation of motion shall be v squared is equal to u squared minus 2g s. So now the most important thing is here you have to understand actually you just have to understand what sign to use when the body is either moving upwards or whether it is under free fall. Alright, so when a body is projected vertically upwards, it's subjected to a retardation of 9.8 meters per second squared. So that means A shall be equal to a negative g, which is equal to negative 9.8 meters per second squared. Alright, so now let's look at some important terms. So the first term we're going to look at is maximum height. So it's an important term here. So what is maximum height? So when a particle is projected vertically upwards, the final velocity is 0 meters per second and its height. So at its maximum height. So that means that basically before a body begins falling back down, it means that it actually stopped moving. So it came to a place of rest. So that final velocity is 0. So therefore, from our equation, from the third equation of motion, because right now we're looking at us throwing a body, projecting it vertically upwards, we're going to use a negative here. So that's why we have a negative. And where there is s, we substitute that with a h because we are looking at a height. So our distance shall be in a form of height. So we can put an h where we have the s. And this minus simply means that the body is moving vertically upwards. So basically, from this equation, we can actually see that definitely if we make v 0, v means that means that right now the h we are looking at is the h at the maximum height. So if we make h the subject, you can actually say that h max shall be equal to u squared over 2g. So therefore the formula to find the maximum height shall be equal to u squared over 2g. At maximum height, the body is momentarily at rest. Thus v is equal to 0 meters per second squared. So if you want to find a maximum height, just make sure to put v as 0 and you'll get it. So and then your h will be the maximum. So time to reach maximum height. So now we're looking at t. So now we're going to look at the first equation of motion. And remember, right now still since we're still looking at a body being projected vertically upwards, we're looking at a negative g. So that's why we have a v is equal to u minus gt. So now we basically have to make t the subject. But of course at maximum height, again, since we're looking at time to reach maximum height, we have to make v 0 because the body is again momentarily at rest at that time. And therefore if we make t the subject, we actually say that t shall be equal to u g, and this is how you find the time taken to reach the maximum height. How about the time of flight? So time of flight is basically the time it takes for the body until it lands. So this is found as t being equal to 2u over g. The time of flight, which is the time it takes until the particle hits the ground, is twice the time taken to reach the maximum height. So basically when you're asked to find the time of flight, you just multiply a 2 to the time taken to reach the maximum height. So time taken to reach the maximum height was t is equal to u over g, and this one shall be 2 times u over g, and that's how we get the time of flight. Alright, let's look at some questions here. So this is question number 1. So the question is saying a stone is thrown vertically upwards with a velocity of 21 meters per second. Calculate the maximum height attained by the stone. So that's our question number 1, and part 2 says the time the stone takes to reach the maximum height. So how do we solve this? So it's basically easier if you just sketch. So here is our sketch here. So you're going to imagine that the body moves. So we're going to imagine that A was the beginning point. The body went until it reached a height of a height where there is a point B. And then that when the body came back down, it landed at a point C. So this is how we sketch that. Now we can see that h max is now representing the maximum height. So maximum height is the distance from the vertical floor to the point B. And now we can see that the initial velocity as we've been given is 21 meters per second. And then the final velocity on landing is actually unknown. What we know is the v value at B is actually equal to 0, but then we don't know the final velocity at the point of landing. So now all those are going to be important. But now we're being asked to find the maximum height attained by the stone. Now we can see that there are two parts to this. You can actually see that there is this part here where we're looking at the body moving upwards. And then there is the second movement where the body is coming under free fall. So movement from B to C is actually under free fall, and movement from A to B is the body being projected vertically upward. That's why we have a negative g here and we have a positive g on this other side. But this will make more sense as we do different numbers. So being asked for the maximum height attained by the stone, we've just seen that at maximum height v is equal to 0 meters per second. So that means the value of v at this point B here is 0. So now we need to find maximum height. Now we can find that h max. Now we need an equation of motion where there is actually an s involved, where we can convert that s into an h, or you can actually use the formula that I'd actually given you for maximum height. But basically we're going to make v 0, and then we're going to substitute s for h max, and then we remember from our equation of motion. So now we can see that 21 squared is 441, and then 2 times 9.8 is 9.6. So making h max the subject, we can actually see that h max shall be equal to 441 divided by 19.6, which is equal to 22.5 meters. So that's basically how you attain the maximum height. So you can either use this, so I basically chose to derive it from scratch, but you can actually just use the maximum height formula that we'd actually derived before. Alright, so therefore the maximum height attained by the stone is 22.5 meters. Now in part 2 we are being asked to find the time the stone takes to reach the maximum height. Now we remember deriving the formula for that. We remember that from v is equal to u minus gt. At maximum height v is 0, and then actually you can actually use the formula we actually derived for the time taken to reach maximum height, which is t is equal to u over g. But now we're going to just derive it from scratch, because we know that the same thing is true, that at maximum height v is 0. So we put a 0 there, make t the subject, and t shall be equal to 2.14 seconds. So therefore the time the stone takes to reach the maximum height is 2.14 seconds. Alright, moving on to question number 2. We're being told that a stone is dropped vertically from the top of an overlapping cliff and hits the sea 3 seconds later. Find the speed of the stone as it hits the sea and the height of the cliff. So this is what we're going to sketch. So we're going to imagine that this vertical line right here represents the sea, and then this is the ball before it is dropped. Then you can actually see that the distance the stone moves until it hits the ground is what we call its maximum height. So basically now this is the body under free fall, so it actually means that the value of g is positive. And then you can actually see that because the ball was being held before it actually dropped, before it was actually released, so that means that its initial velocity is equal to 0. So u is equal to 0 meters per second. Then the value of v is with what we did not know, and that v is going to represent the velocity as it hits the sea. So at the point where the stone is dropped, u is equal to 0 meters per second. Now we can easily solve this part and find v by using the first equation of motion. We know that v is equal to u plus gt. So now we're going to have a positive g because this is the body under free fall. So v is equal to 0 plus 9.8 times 3. Then you can actually see that v is going to be equal to 29.4 meters per second. So now we need to find the height of the cliff, and how we're going to do that? We're going to use the third equation of motion. So remember again, the value of g is positive, so that's why we have a v squared is equal to u squared plus 2g s. And now where there is s, we're going to substitute that with h, and that h is going to represent our h max. Now in this case, in this situation, the only way you can know what the h max value is to get the real maximum height is you have to state that the value of u is 0. So since the initial velocity is 0, so this makes sense that the body, so that means that the h value we're finding is from when the body was not yet released. So that's why this will actually give us the h max value for this situation. Then you can actually say that h shall be equal to 44.1 meters. So therefore the speed of the stone is 29.4 meters per second and the height of the cliff is 44.1 meters. Alright, let's look at question number 3. So we're saying a ball is projected vertically upwards and then it returns to its point of projection 3 seconds later. Find the speed with which the ball is projected and the greatest height reached. Alright, so this is the ball that we actually have. This is just an illustration of what we have. So now we're looking at the ball moving to a maximum height, and then its initial velocity is u, and then its final velocity is v. So now in this question, the only thing that we have been given is we know the time of flight. So the time of flight is the point the ball moves until it comes back or until it lands. So now we know what the time of flight is. So the time of flight is given as 3 seconds. But we know that the formula of time of flight is t is equal to 2u over g. So we can actually use this formula to find the value of u. So from this, when we substitute in the value of 3, we have 2u over 9.8. Then when we make u the subject, we actually see that u shall be equal to 14.7 meters per second. So now therefore the ball was projected at the speed of 14.7 meters per second. So now next we need to find the greatest height reached. Now we're going to basically use the formula of maximum height. Now remember at maximum height v is 0 meters per second. So now using the third equation of motion, now remember that now since we are looking at the point of the ball moving upwards until it reaches that maximum height, we're going to make g a negative. So that's why you have a v squared is equal to u squared minus 2 gs. And then where there is s, since we are making the v a 0, we're going to substitute that with h max. Then you can actually say that h max shall be equal to 11.025 meters. So therefore the maximum height attained by the stone is 11.025 meters. Alright, question number 4. We're being told that a ball is projected vertically upwards with a speed of 20 meters per second from a point, a height h above the ground level. If the stone hits the ground 5 seconds later, find the value of h, and part 2, the velocity with which it hits the ground. Now this is slightly different because now we're looking at a ball thrown from a certain height above the ground. So this is how basically we can illustrate this. So now we're going to imagine that what we have here, so this is basically an illustration of the height of the ball above the ground. So it's actually projected now not from the same vertical floor to where it lands, but it's actually projected from a certain height above the ground. So this is how our illustration is now going to be demonstrated. But in this case, it's going to be different because now we're going to have to consider the height of the point from which it is actually projected, which is actually this. So small h here represents the height from which it's projected from above the ground level. And then maximum height value will actually be this remaining height from the point on the above the point where it is projected to the highest point reached. So this is what's going to represent our maximum height. So now in this case, we're being asked to find the value of h. So we want to find that height above the ground or the height of the cliff from which it has actually been projected. So I want to find this height here. And how do we do that? Now you can actually see that this is what we end up having. Now we can actually see that the time of flight has been given as 5 seconds. So we know that t is 5 seconds and u is 20 meters per second. The easiest way we're going to find the value of h here is by considering the whole motion a, b, c until the point it lands. So how we're going to do that? With reference to the point of projection, h shall be equal to a negative h. Since in this case we're projecting from a height above the ground, we're going to consider the h to be a negative h. Now this is what we do every single time a ball or something is projected from a certain height above the ground. So you make the value of h to be a negative h to consider that reference point. And now we're going to use the second equation of motion, and of course we're going to be looking at a negative, and that's because we are starting from this beginning point. Now that is because that our initial velocity that we're looking at is we're looking at the initial velocity at the beginning, as we move upwards. So that means we're going to consider this as a negative. And now the reason we use the second equation of motion is because we're looking for the value of h, where we're going to substitute it as a negative h, and then we know what u is. U has been given as 20, and then we also are looking for the we actually know what time it takes. We know the time taken is the total time of flight. So this is going to be basically the easiest equation to use to find the value of h. So now we're going to substitute in. So we're going to, where there is s, we put a negative h, so we end up having that. And then what we can see that negative h shall be equal to that, and then we end up having 9.8 times 5 squared is 245, and then you can see that 245 times a half is 122.5. So 100 minus 122.5 is negative 22.5, and then you can actually see that the h value shall be equal to 22.5 meters. So we now know the height above the ground is h for this question. Alright, so next we want to find the velocity with which it hits the ground. But before we find the velocity, it's going to be important first find what that maximum height is. And how we're going to find the maximum height. We remember that from the formula, h max is equal to u squared over 2g. So we can actually say that we end up having 20 squared over 2 times 9.8, which is equal to 20.408 meters. So we know what the value of h max is. Now, since we know what the value of h max is, now to find the velocity with which it hits the ground in this case, now we're going to consider the motion bc. Alright, so in such an example, when we're dealing with finding the velocity with which the ball hits the ground, now this case is going to be different. Now to find it, you will have to consider the motion from b to c. So that's going to be the easiest, so we can find the v. And now in this case, since we're going to consider the motion bc, some things will be different. So our v value is going to remain the same, but now we're going to begin with the velocity at the point b as our initial velocity. So that means our u is going to be equal to 0 meters per second, since we're going to basically only consider the motion from b c. And now we can see that our gravity shall have a positive value in the motion from b to c. Right, so now that we know what we now we're considering, we can see that u shall be equal to 0 meters per second. So v is unknown, and now we know what the h max value is. H max is 20.408, and now we have to know the exact height of bc. So to get the exact height moving from b to c, it's going to be h max plus h, and that's what we're going to consider in our formula. Alright, so now we're going to consider the third equation of motion, and that is what's going to be most useful, since we know what we're looking for, a v, and we know what u is, and we know what s is. And then when we substitute in our values, we can see that the s value is going to be equal to h max plus h to get the general height from b to c. And then of course we've seen that now the g shall be a positive, since the motion from b to c is a free fall. So we're going to have the u as 0. So you can actually see that 20.408 plus 22.5 is 42.908, and 2 times 9.8 is 19.6. So 19.6 times the value in bracket is going to be equal to 840.9968. So v squared is going to be the square root of 840.9968, of which v shall be equal to 28.99 meters per second. And this can be easily rounded off to v being equal to 29 meters per second. So therefore the height above the ground h is 22.5 meters, and the velocity with which the stone hits the ground is 29 meters per second, and that's what they wanted. So let's move on to another question. So this is going to be our question number 5. So we're being told a particle is projected vertically upwards at 30 meters per second. So calculate how long it takes to reach its maximum height. And then we're also being asked the 2 times at which it is 40 meters above the point of projection, and the 2 times at which it is moving at 15 meters per second. Now something important here is when a ball is moving upwards, it's obvious that there will actually be 2 different times at which it can be at a certain height above the ground, because imagine you've thrown a ball from a certain base, let's say here, and then there is a height that is 40 meters above the ground. So when you throw the ball and it passes through that point, so you actually see that there will be 2 different times where it will actually be 40 meters above the ground, and that is what we are looking at in this case. And that is going to be important. And obviously there will also be two different points it will be moving at a certain speed, because as we're projecting it, before it attains v as 0 at the top, it will also gain another speed before it hits the ground. So there will also be two different points where it can have two different speeds. So that's what this point of the question is looking at. So let's solve this. So we're going to sketch our diagram. So you can actually see that the body is moving at 30 meters per second initially, and then this is how we illustrate it. Now we need to first know how long it takes to reach its maximum height. So remember, the formula to find time taken to reach maximum height is t is equal to u over g, of which t is going to be equal to 30 over 9.8 and t shall be equal to 3.06 seconds. Therefore the particle takes 3.06 seconds to reach its maximum height. Now the next part is we're being asked to find the two times at which it is 40 meters above the ground, and that's what we're going to be looking at. So now we need to find those two times where the value of h shall be equal to 40 meters. Now we know what u is 30, but we don't know what t is. Now we need to use an equation of motion that allows us to find those two times. Now definitely we need to use the second equation of motion, but since we're beginning with the initial value of u from the point where the ball was initially being projected, so we're going to consider a second equation of motion where the g is a negative. So that means there's going to be an upward motion involved at the very beginning, so we're going to have a negative right there. So when we substitute in that, we can actually see that h shall be equal to 30t minus a half 9.8 times t squared. So now we can actually find the t. So we just have to place the 40 where we have the h now. Then 40 shall be equal to 30t minus 4.9t squared. And therefore we form a quadratic equation which we can solve using the quadratic formula. So using the quadratic formula, we can actually say that we'll get either t being 4.163 seconds or t being equal to 1.96 seconds. So this shall be the two different times. So therefore the two times the particle is 40 meters above the ground are 1.96 seconds and 4.163 seconds. So obviously the lowest time is going to be the first time it was the height 40 meters above the ground, and the bigger time is going to be the second time it was the height 40 meters above the ground. Now part 3, we are being asked to find the two times at which it is moving at a speed of 15 meters per second. Now how do we do that? Now we need to find the two times where v is 15 meters per second. So we again know that u is 30 and then t is unknown. So now we need to find the height where v is 15 meters per second first. So that's going to be very important first. So we need to first consider and find that height. So at which height is it 15 meters per second before we actually do what we did in the former number. Now we're going to use the third equation of motion to find that height. So we're going to use v squared is equal to u squared minus 2gs to find that value of h. So now we can see that if we make h the subject, h shall be 675 divided by 19.6, which is equal to 34.439 meters. So now after we've known that height, now we can do what we did in part 2. Now we can find those two different times where now the height is 34.439 meters. So now from the second equation of motion, s is equal to ut minus a half gt squared, we substitute in the value of h right there, and then you can actually see that we'll end up having that. So we have another quadratic equation which when we solve with the quadratic formula, we shall have either time being 4.59 seconds or time being equal to 1.53 seconds. So therefore the two times the particle is moving at 15 meters per second are 4.59 seconds and 1.53 seconds. So the trick here to the third one is before you are able to know the exact times of which it's moving at 15 meters per second, you have to first determine the heights where it is moving at 15 meters per second, and that's what made this part easier to do. Alright, now when we move on to the next one, this is part number 6, question number 6. So we're being told that a particle is projected vertically upwards from ground level at a speed of 24.5 meters per second. Find how long after projection the stone is at a height of 19.6 meters above the ground for the first time, for the second time, and part 3, for how long is the stone at least 19.6 meters above the ground level. And as you can see, part 1 and part 2 make sense because definitely there will be two different times that the stone can be at a height of 19.6 meters above the ground. So let's solve this. So this is what we have as our illustration right there. Then part 1, we need to find the 2 times where h is 19.6 meters, where we know u and we know what t is. So definitely we're going to use the second equation of motion, where we're going to put 19.6 where we have the h value, which is s. Then we end up having that. So after solving this with quadratic formula, we can actually say that we'll get either time being 1 second or time being equal to 4 seconds. So therefore the stone is at a height of 19.6 meters above the ground level for the first time after 1 second, and for the second time after 4 seconds. Now actually, by doing it this way, we've actually already solved part 1 and part 2 in the most simple way. So this is definitely the 2 different times. So in part 3, we're being asked to find how long the stone is at this 19.6 meters above the ground. Now this is going to be easy. So we're being asked to find how long the stone is above. H is 19.6 meters. So this is easy. So it's basically as simple as finding the interval between the times the stone is above 19.6 meters the first time and the second time. So that's how we're going to do it. But now we already know the answers to that. So now the interval is basically 4 seconds minus 1 second, as we've actually found in equations 1 and 2, and definitely the answer is 3 seconds. So therefore the stone is above the height of 19.6 meters above the ground level for a duration of 3 seconds. Alright, so in the introduction to vertical motion under gravity, I basically talked about some examples that involved one particle, and you can observe that by going through the video. So today we're going to ask ourselves, what if there are 2 particles involved, 2 particles that probably meet mid-flight and all that, or land, or all that. So how do we do such numbers? So today let's look at 2 particles with vertical motion under gravity. Alright, let's learn something new. So question number 7, we're being told that a ball is thrown vertically upwards at 25 meters per second from a point P. Then we're being told that 3 seconds later a second ball is also thrown vertically upwards from the point P at 25 meters per second. So being told to calculate how long A has been in motion when the 2 stones meet, and part 2 we're being asked the height above P at which A and B meet. So now this is slightly different, but now we're also going to illustrate this. So now this can best be illustrated this way. Alright, so now here is our illustration. So now we have those 2 balls being thrown. Now we have the ball A and the ball B, which are thrown from the same point P, and we're being told that there is a point where they both meet. So now this dot here is representing the point of meeting, and the ball projected from the point P, and they will have a point of meeting. So the ball A is thrown the first time, and then the ball B is thrown, and we're being told that they meet in the air at a certain point. So now the most important thing here to consider is the height at which they meet in the air, and we're going to call that height h. Then you can actually see that we are being thrown at the same initial speed. So that means UB shall be equal to 25 meters per second, and UA is also 25 meters per second. So now we can actually see that now the easiest way to solve this is, now there are many unknowns. In part A, we are being asked to find how long A has been in motion when the 2 stones meet. So we're going to let TA be time taken by ball A to the meeting point, and then also we're going to let TB to be the time taken by ball B to the meeting point. Now also we can actually see that the values of the initial velocities are the same. So UA is equal to UB is equal to 25 meters per second. And now we are also told that the second ball, which is ball B, was only projected 3 seconds later. So that means the value of TB shall be equal to TA minus 3, since the ball B was thrown 3 seconds after the ball A was thrown. So that means TB is TA minus 3. So at the point of meeting, the 2 balls are at the same height, and that is the most important thing in this question. So that means that HA is going to be equal to HB is equal to H. So the heights have to be the same at the point of meeting. So now let's solve this. So we're going to first find height A, and we're going to use the second equation of motion to solve that. So we can actually say that HA shall be equal to 25 TA minus a half into 9.8 times TA squared. So now we can actually say that HA shall be equal to 25 TA minus 4.9 TA squared, and that's going to be our height for the first ball, which is ball A. Now we also need to find the height of the ball B, which is going to be HB. So HB shall be equal to 25, and now remember that the time difference is now the time B, we shall represent it as TA minus 3. So instead of TB, we're going to substitute that as TA minus 3. So 25 into TA minus 3 minus a half into 9.8 times TA minus 3 squared. And then HB shall be equal to that, and then we can actually see that if we simplify this, HB shall be equal to 54.4 TA minus 119.1 minus 4.9 TA squared. So that's it. But now we also remember that the value of HA shall be equal to the value of HB. So that means you can equate these two different values. So now we have 25 TA minus 4.9 TA squared is equal to 54.4 TA minus 119.1 minus 4.9 TA squared. And then now when we collect like terms, you can actually see that these 4.9 values cancel. So this and this cancel, and then we are left with these other values. And then we can actually say that we can take this 119.1 to the other side, and then we can have 54.4 TA minus 25 TA, which is 29.4 TA. And now we can easily find the value of TA. So TA shall be equal to 4.05 seconds. So therefore the ball A has been 4.0 seconds in motion before the two balls meet. Now definitely we can now also find that height above P where the two stones meet. So now we've been told that HA, we know that HA is equal to HB is equal to H. So now we can simply use the first equation that we had actually found to find the value of HA. So HA shall be equal to that. So we're going to substitute in the time TA in to find HA. And therefore we can see that HA shall be equal to 20.88 meters. So now that we know HA, it means we also know all the other different heights because they're all equal. So therefore the height above P at which A and B meet is 20.88 meters. And that's how we work out such questions. Now, number 8, we're being told that a particle is projected vertically upwards with a velocity of u meters per second. Then we're being told that after t seconds, another particle is projected vertically upwards from the same point of projection and with the same initial velocity. So we're being told that prove that the particles collide after t over 2 plus u over g seconds, and hence show that they will meet at a height of 4u squared minus g bracket gt squared over 8g. So how do we solve this? It's basically the same as the former question. So let's first sketch it to have a better understanding. So these are two balls or two particles, but let's call them A and B to make it easy because we've not been told what they're called in this question, but we can choose the name for them. I've chosen to call mine A and B, and obviously the rules remain the same, that if they meet at the same point, so that means at the point of meeting the height is the same. Alright, so we've been told that the balls have the same initial velocity. Alright, so we won't let TA be time taken by particle A to the meeting point, and then TB to be the time taken by particle B to the meeting point. And definitely we've actually been told that now all of them have the same initial velocity. So that means UA shall be equal to UB, and that shall be equal to U meters per second. So we're just going to have the same initial velocity. And then we've been told that after t seconds the other particle is projected. So that means that the time for the second particle projected, which we've chosen to call B, that time TB shall be equal to TA minus T to represent that unknown time difference. So the difference is going to be TA minus T. So at the point of meeting, the two balls are at the same height. So therefore HA shall be equal to HB is equal to H. So let's first find height A, and we're going to use that second equation of motion. So we're going to substitute it right there, and then we can actually see. Now what we're going to do is, because we're just proving this equation, we're going to leave the G as it is. You're not going to put a 9.8 there, since I've seen that there is a G in the final proof. So we're going to leave the G untouched. So that's why we now end up with HA being equal to UTA minus G over 2 TA squared. And now instead of having UA, we can actually see that all of them can be generalized to be U, because they just have the same initial velocity. So that's going to be the height of the first particle, and then from find the height of the second particle, which is B, we're going to have that. And then when you open those brackets, this is what we end up with. Now you can see that the time difference, the time of this is TA minus T, which is what represents the time TB. And then this is what we end up having. So when we simplify this, now we need to simplify this further. We've opened those brackets. So when we simplify this further, we end up having HB being equal to UTA minus UT minus G over 2 TS squared plus GTA T minus G over 2 T squared. But we remember that HA is equal to HB. So that means we can actually equate both of them. So we can equate HA and HB. And then we can actually see that some values will, we'll just have to equate some values. So you can actually see that this and this will cancel. And that's what actually happens. Then you can actually see that this and this will also cancel. So what do we remain with? We remain with 0 on this side being equal to minus UT plus GTAT minus G over 2T squared. And then now we're going to rearrange them slightly differently. And now remember that now we want to prove something. So I want to prove the time A. Now we can actually see that now when we find the LCM right here, so the LCM is going to be equal to 2, and then when we have this 2 divided by 1 is going to be equal to 2. That's why we have a 2 multiplying this, and then we have 2 divided by 2 is 1, and then 1 times this is going to be equal to, we're going to leave it as GT squared. So now this is what our equation becomes. Now to make, when we make TA the subject, TA shall be equal to 2UT plus GT squared over 2G. So now when we separate the 2GT in between the two different numerator values, this is what I end up having. So I end up having TA being equal to U over G plus T over 2. And thus we've actually proved the time taken for the first particle. So therefore the particles collide after T over 2 plus U over G seconds. And that's our first proof. Now next we have to find the height h. Now we know that HA shall be equal to HB is equal to h. So we can actually first find HA, and that will enable us to know the rest. So now we're going to substitute in the time A that we have actually just derived there, because the time A shall be equal to T over 2 plus U over G. And then we can actually see that when we simplify this by opening brackets, you can actually see that now at the bottom here we have 4G squared, and then this brackets remain squared, and that's what we end up having. And now when you actually expand those, this is what we end up having. So this expanded is GT squared plus 4UGT plus 4U squared. Then when you multiply this in, this is what we end up having. Alright, so now next we can actually see that next we can actually open the brackets. Now pay attention to the negative sign that we actually have there. Now you can see that when you open these brackets, we will have a negative GT squared minus, so this plus will become a minus. That's what we have there, and this will also become a minus. So pay attention to that because it's easy to make a mistake there. And then next we're going to find the LCM of these, and then the LCM of the 2 is 2G and 8G is 8G. Then 8G divided by 2G is equal to 4, so we have 4 times the values at the top, which makes it appear like that. And then 8G divided by 8G is 1, so 1 times the values here, the values just remain as they are. And then we can actually see that now when you open the brackets, we can actually see that we have 4UGT plus 8U squared minus these other values. So now we're going to simplify this further, and then actually we can say that 8U squared minus 4U squared is equal to 4U squared, and then you can actually see that 4UGT and this cancel, so they will remain with 4U squared minus G squared T squared. And therefore we've actually proved our equation. So therefore H is 4U squared minus bracket GT squared over 8G, and therefore the particles will meet at a height of 4U squared minus GT squared over 8G. Alright, now there is an exercise for you. These are some trial questions that you can actually try out, and this will actually enable you to have a better understanding. And then just make sure to actually do this and then compare your answers to what you have there, and I believe that after you've tried this out, you'll have a far better understanding. This is question number 4, and those are the answers. And then lastly, this is question number 5. So just try this out and test yourself to see how far you've understood today's topic. Thank you for watching. Again, thank you so much for watching this video. I hope the video really helped you. If it did, feel free to tell me below in the comments. I'll make sure to get time to read through your comments and to reply to you. And also, if you're new to this channel, I encourage you to join the community by subscribing, and then make sure to hit the notification bell so that you get updated every single time I upload a new video. Again, my name is Emmanuel Olega. Thank you so much for watching. See you in my next video.